pleasure to introduce our first partner session speaker. It's Dr. Kyuwoong from Qualcomm Research Career Office. He's a colleague of mine, and he and his team, they've been doing pioneering work in the field of audio, and more recently applying machine learning and federated learning to audio type of applications. So it's going to be very interesting overview of the machine learning, tinyML, and audio. Okay, the stage is yours.
I will talk about we have the group of doing always-on machine learning and on-device learning and training personalization, and also the framework to do all those things in a very low-power way. So I will briefly explain some of our work on this area. Okay. So the first thing is a broadcasted residual learning. So this is a network architecture we proposed that we see that it shows a very good performance in audio use cases. Okay. So if you think about efficient network, the handcrafted network like a mobile net, a shuffle net, efficient net, there's a lot of these things are happening in the computer vision side, but there are not much for the audio side. These networks usually having that repeated blocks and residual learning, and that's why separable convolution. So because these networks show very good performance in video, vision, and image, so people try to use the same CNN architecture for audio processing. So some uses like a 1D temporal convolution or 2D convolution. But both of these approaches has its limitations. 1D convolution, it is very efficient, that's good, but for frequency axis, it does not support the translation invariance. So that is a little bit of problem, because if the sounds frequency or shifted upper or lower, then it treats it differently. So 2D convolution can support the problem and solve the problem, but it requires more computation compared to the 1D. So if there's a good hybrid or approach that using that getting both of these good factors, then there can be a solution. Okay, so this is the idea we have. So conventional residual learning, each residual block have a couple of layers inside. In our case, we start with 2D input feature map and perform one layer, and then we average it over frequency axis and get a temporal feature and perform 1D convolution here. And then later, it can be extended into 2D features. We don't need to allocate all these memories. It can be can be broadcasted into 2D during when we add this residual output with this shortcut connection. So in equation, it can be written as like this. 2D input is a overall layer and frequency-wise pooling, and another convolution, and it is broadcasted to the 2D and added with the speed connection. So this is the architecture here. So the first convolution, we do frequency depth-wise convolution, and here we also apply the subspectral normalization. So this is subspectral normalization, meaning that for some part of the spectral groups, we do normalization. This kind of group normalization over frequency axis. So that gave us a little bit better distinction for different normalization for different frequency bands. And then it is converted to 1D temporal and performed the convolution and added again. Okay. And there is one more skip connection is added here. Okay, this is the basic architecture. And the total memory, number of parameters are less than 10K. And this is scalable. So this is the tau is 1, and if tau is increases, we increase the channel width with that scale ratio. So this is our performance here. This is the number of parameters. This is the accuracy. So if you see here, our BC ResNet scale 1 to 8 all showed better accuracy with the same number of parameters over such as Matchbox.net or DS ResNet, TC ResNet, or standard ResNet. It showed BC ResNet showed a much better performance with the same number of parameters than these conventional architectures. It is not only saving the number of parameters, it is also saved the number of computations. So if you see the MAC versus some accuracy, then this ResNet is also outperformed the others. And these results are we got from the Google speech command, the keyword keyword detection experiments. And by changing the architecture a little bit, and then we applied it to another task. It's a DK's challenge 2021. Now, this one is a low complexity acoustic scene classification task. And as you see here, among these four, the three are from our submissions. Okay, we got a very good accuracy with a good margin from the others. Okay, so there was one approach, and these are another network architecture for keyword detection. So for keyword, we can, for encoder, we use the recurrent neural network, and then we apply the attention to get the final score for the keyword. But as you know, the keyword is a word, so it has sub-components. It has some structures, and we'd like to let the network to discover it. So we made the attention block to have multiple heads, and then we hope that those different heads focuses on, attends on different regions of the keyword to give a better performance. So this is the result. So if you see the first diagram is a spectrogram, and the attention rates over time is overlaid with a spectrogram. So when we have a single attention head, so it attended this part of the keyword. And when we increase the number of heads from 1 to 4, in this case, we expected that these heads to focus other different parts of the keyword to make a best judgment. But as you see in this example, many of those attention heads actually overlapped because they don't have any objective or constraints to focus on different parts. So many of them focuses on the same parts. So to avoid this problem, we added another constraint into the loss function to make these attention heads, attention weights to be orthogonal from each other. So they need to be different. So if you see this diagram, then these different types of lines shows the different attention focus of different heads. And as you see, most of the attention heads focuses on different parts of the keyword, and that improved the accuracy. So here, both this one and this one uses 4 heads, same network architecture, same computation. But by giving with this regularization to obtain the different part of the keyword, the false alarm rate is reduced from 5 to about 4 per hour. So there is a good improvement with these constraints. Okay, another thing is that it will be good. Most of these always-on applications can be used by a certain person or certain environment. So if it can be personalized after deployed, that will be very good. But there's a problem. So because this is a tinyML, so training usually requires a lot of data, computation, and memory, and complex runtime that supports backpropagation and also all those optimization strategies. So that's a kind of quite complex. So we proposed another way of doing it. So it's like a human a little slow for a new task, but after several experiences, becomes quicker with less effort. We assume that the primary path of the processing is identified and done in a simpler way. So this is similar. So instead of updating the model parameters with backpropagation, we start with a little bit bigger model and just select some parts of the network that is best for that person. So that way, we prune out the others, the irrelevant ones from certain person. They can be removed, and only relevant parts of the network for the person can be remained. And we hope that it shows similar performance as the big model with this small one for the certain person. So the overall process is that we trained on gating module. So this gating module is depending on the input. So if there's an input and it goes through the network, and those activation values also feed into the gate module, and gate module determine which part of the layer, for example, in this case, channels, to be activated to process this input correctly. So this is the gate module. And we want to make a network that customized for a certain person. So we'd like to make these gating patterns not depending on the input itself, it to be depending on the certain person. So if there are 5 utterances are given for a certain person, and there will be 5 different gating patterns, but we'd like to make them to be similar as a prototype. So there is also a prototype generator. This is similar to the few-shot learning case, where the prototypical network is used. So this is during training. At inference, with this only gating module will determine which part of the network. So at first when it is deployed, this whole network, the gate module will determine which part of the network to be used, and after that, only the subset of the network can be actually loaded into the device for inference, and will give a similar performance with much smaller memory size. A little bit more detail of the loss function here. These are the Z is the gating pattern, and we'd like those gating patterns to be centered around its prototype. And also, this is a target pruning rate. If we have certain target, like we'd like to make the network is a third of the original one, then we can give that ratio in this loss function. Okay, this is the result for SIPA 10 and 100 and Qualcomm Q-speed dataset. The upper one is a SIPA 10 and 100 dataset. We assume that each class is a kind of a person, and so these are the network for certain class. So if you see here, the performance is a little bit better sometimes and similar, and the utilization rate is reduced to 37%. Is better than other ones. And the next experiment, it is really for personalization, because with these keyword data set, we made a personal keyword detection performance, because each person is keyword detection. If it is used by one person, then it is a personalized application. If you see here, utilization ratio is reduced a third, and it maintains the accuracy of the full network. And if you see here, this one, the orange case, in this case, if we didn't give any regularization, that those gating patterns need to be clustered around a prototype, then this is the result. And if we give that regularization, then all those gating patterns gathered around the prototype. And that one, with regularization, gave a much better performance than without one. Okay, that's the network architectures and personalization method we developed for these tinyML devices. And I'd like to introduce briefly about these tinyML, where it is happening at the Qualcomm Snapdragon chip. So if you see these Snapdragon chip architectures, there is a Qualcomm sensing hub. This is a low power island that a lot of sensors are connected, and also the machine learning accelerators are there. So these are the platform for tinyML in Qualcomm. And also, if you see the software package, there's a EAI add-on that provides the very lightweight ML runtime, and that is optimized for the ENPU hardware accelerator. So these are the framework for tinyML in Qualcomm. So, any questions?
Yeah, so it's a very interesting presentation. Thank you, Kyuwoong. A couple of questions. I think on the last topic, on the tinyML Snapdragon, I think you mentioned the sensor island, the sensor hub, and then the AI and the ENPU. What kind of classes of algorithms or functions can you run on that island and on the ENPU?
ENPU, you can run many kinds of algorithms, and so basically the AI, or these are like other machine learning toolkits. It receives the Onyx version of a model that is originated from PyTorch or TensorFlow. It is first converted to Onyx, and then it is converted into the AI format, and it can be run at the local sensing hub.
So basically what you're saying, if people develop their models using TensorFlow or PyTorch, then they should be able to run them on the ENPU, correct?
Yeah, that's right. Because still it is a deep embedded system, so they need to consider the model size or memory size, or if not all of the operators are supported, they need to use alternative operators or architectures. But basically, yeah, that's true. You can run.
Yeah, no, I think this is quite impressive. So related to this, are there any limitations in terms of like model sizes or that people can or cannot run on this hardware?
You're asking about the size of the models?
Yeah, for example.
For example,
let's say if people have a model like, let's say, 5 megabytes of memory, will they be able to run it there? Or 10 megabytes of memory?
It's like the size of like MCU, if it's several kilobytes, will be, okay. I think will be okay, but megabytes will be tough.
Okay, sounds good. And then on the prototype-based personalization pruning, I think you made a comment that by doing so, you're not getting any performance hit. Can you quantify it? Like I think you showed the table at some point. Is it the performance hit there?
So performance is it is actually much better than all other ResNet-based approach for these QoS pattern. So it's actually SOTA in this area, this architecture.
Okay. And then I think related to the first part of the presentation, you mentioned that there are different parallels to what people use in the computer vision. And then we know that many companies, many groups use spectrograms, and then for audio. Can you comment like what is the state of the art in this field? It's companies using spectrograms and then kind of convolution networks to do recognition, or people use kind of more traditional 1D type of models? Like what is happening in the industry?
Some actually uses just the waveform itself. It's kind of an undetermined approach. The PCM sample itself is given into the 1D convolution network, and it performs all those convolutions to perform the classification. Sometimes more commonly, people are using log-mass spectrogram as input to this network. And we also use that for these experiments, and it showed best performance. Not only this, as the set, also the case competition.
Well, thank you, Dr. Hwang, again, and thank you also for your patience, for staying with us during this morning. Yeah, thank you.
We want to thank especially our strategic partners who have made it possible. We have our executive sponsors, ARM, the Software and Hardware Foundation for tinyML, then at Impulse tinyML for all developers, Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous, Sentient end-to-end deep learning solutions for tinyML and Edge AI, then Platinum sponsors, Reality AI, add advanced sensing to your product with Edge AI, tinyML, and then Renaissance, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge, Maxim Integrated, enabling edge intelligence, Seed Studio, the IoT hardware enabler, SensiML, build smart IoT sensor devices from data, SynSense, build sensing and inference hardware for ultra-low power embedded mobile and edge devices, and our silver sponsors, Aeon Devices, Deep Light, EMSA Visual Sense, Greenwaves Technologies, Gravity Inc., HODG, Imagimob, Kixo, Rixen Technology, and SAP. So thank you everyone for staying with us today, and see you tomorrow.